We've been talking about gases, and we had previously talked about stoichiometry and chemical reactions. So now we're going to combine those two ideas. If we have gases as reactants or products, then we will often specify the quantity in terms of a volume at a particular temperature and pressure. So we can use the ideal gas law to get the number of moles from the pressure, the volume, and the temperature. And then if we need a volume of gas at the end, we can calculate the volume using the moles from the grams to moles part of the stoichiometry calculation. If the gases are at STP, it becomes much simpler because this molar volume of a gas is true for any gas at STP. 1 mole is equal to 22.4 liters. So this is our normal stoichiometry chant, grams to moles to moles to grams. With gases, we may change up one or both ends and need the pressure, volume, and temperature of a gas at either end or both ends. So let's do a couple of examples of that. In the following reaction, 4.58 liters of oxygen was formed at P equals 745 millimeters mercury and T equals 308 Kelvin. How many grams of Ag2O decomposed? So we'll go through here and look at the numbers and look at the question. This is stoichiometry. There's a chemical reaction happening, and so I like to use the chemical reaction, the equation there, to organize the numbers. So here we have a volume of oxygen. So under oxygen, I'm going to write what its volume is. And then we also have a pressure and a temperature. Those apply most likely to the entire reaction, but they're of interest in terms of this gaseous product. So we're going to have pressure equals 745, and temperature is 308 Kelvin. The question is, how many grams of this reactant reacted to give that amount of product? So, stoichiometry, grams to moles to moles to grams. We're starting with oxygen here because that's what we've got all the information about. We're ending with Ag2O because that's where the question is. Do we have mass of oxygen? No. We have volume, temperature, and pressure. So from the volume, temperature, and pressure, we can use the ideal gas law to calculate the moles. And then we can continue to moles of the other and grams of the other, and we do want our answer in grams, so that's good. So the first thing we'll do is calculate the moles of oxygen using the ideal gas law. So rearranging the ideal gas law, we get N is equal to PV over RT. So we need the pressure. Well, the pressure is not in atmospheres, so we need to convert that. 0.98026 atmospheres. And the volume, well, they gave it to us in liters, so that was kind of them. We're going to divide by R, 0.08206 liters times atmospheres per mole Kelvin. The units there tell us what units we need to use for everything else. And then the temperature, 308 Kelvin. You see that our units are all going to cancel out nicely and leave us with moles. need need to be careful when you do these calculations because you're dividing by a product. If that is messing you up, please talk to me during lab. There's several different ways that you can avoid that problem, and I'd like to help you find the one that makes the most sense for you. One that a lot of students use is to use parentheses down here. So there's my moles. That's moles of oxygen. So now I'm here at my first moles, so I can continue using dimensional analysis. I'm going to convert from moles of oxygen to moles of Ag2O, and then to grams of Ag2O. Again, taking this first unit and bringing it down. So moles of oxygen comes down there. Those cancel. Moles of Ag2O down there, and those cancel. Where do we get the mole ratio?
From the formula.
From the equation, yeah. So there's a 2 in front of Ag2O, so I'm going to put a 2 in front of Ag2O. And in front of oxygen, there is no number, which we understand is a 1. Then we're going to need the molar mass of silver oxide. 107.8 is silver. And there's 1 oxygen. So 231.6. And that's grams is equal to 1 mole. So 231.6 grams for every 1 mole. So we've got our moles times 2 times the molar mass, 82.280 grams, 82.3 grams of Ag2O. Any questions? We've learned a lot of pieces: dimensional analysis, unit conversions, molar mass, molar volume of a gas, ideal gas law, all these different things. And what's important to be able to do is to put those pieces together to solve a problem that involves more than just one tiny calculation. Okay? Here's another gas stoichiometry problem. How many liters of oxygen at STP are required to form 10.5 grams of H2O? Well, again, I think it's wise to go through and highlight or circle the numbers. That's the only number. But what does STP mean?
Standard temperature.
Standard temperature and pressure. So that kind of is a number, isn't it? So I'm going to highlight that too because that's pretty important. And then the question is liters of oxygen. So again, we start out thinking about grams to moles to grams. And I forgot to write my numbers down. So under H2O, I'm going to write down 10.5 grams. And under oxygen, I'm going to write question mark liters at STP. So I'm starting with water, and I do have a mass of water. So I'm going to start with grams to moles. But then at the end, I'm not going for grams. I am going to be looking for liters. It keeps trying to circle things when I try to make that symbol at STP. Could you do this moles to liter calculation using the ideal gas law? Sure you could. But using the molar volume of a gas is much faster, right? And if you've looked at worksheet 6, there are, I think, 3 problems in a section entitled molar volume of a gas, and you should use the molar volume of a gas in those problems. Okay, so I'm going to start with grams of H2O. So I've got 10.5 grams of H2O, and I'm going to convert that to moles of H2O, and then I'm going to convert that to moles of oxygen, and I'm going to convert that to liters of oxygen, because that's what my path up there says. So I'm going to put the units in down here so they cancel out. And then I'll put in my numbers. Well, we've gone over how to calculate a molar mass many times. So I happen to remember this one. Molar mass of water is 18.016 grams. So we'll just write that down. The mole ratio, we're looking at the coefficients from the balanced chemical equation. So there's a 2 in front of H2O, so I write a 2 in front of H2O. There's an implied 1 in front of O2, so I'm going to write 1 there. And then this is the one that we haven't really seen in stoichiometry before. This is where we're going to use the molar volume of a gas. So at STP, 1 mole equals 22.4 liters. That is true only for gases. Some students really latch onto that number, they love it, and they use it for all kinds of other things. Only for gases at STP, but here we have a gas at STP. 22.4 liters per mole. So 10.5 divided by 18.016 divided by 2 times 22.4. 6.5275 liters, or 6.53 liters of oxygen. Any questions?